Bivit now. So welcome. I started without actually recording it, so I'll just quickly record it now. So basically, we're going to do Boyau-Savart, which is a way of working out the magnetic field that's caused by a current flowing through a piece of wire. And I don't justify it. I just say that, and this is what you got to know. Boyau-Savart's law is that the magnetic field is equal to a constant, mu naught over 4 pi, times the current flowing through the piece of wire, which is also a constant, can change from problem to problem, but it's going to be a constant for a given problem. That's a constant times the integral of, and it's the ds, which is the little bit of current carrying wire's length, crossed with r hat, which is a vector pointing from the current carrying wire segment to the point of interest over the separation between the current carrying wire and the point of interest squared. So it's an inverse square law like it was for charges. And we just got to know this equation. This is, if you're looking at this and you didn't come to class, that is r hat, not r arrow. This is r hat. It's not just vector, it's the little unit vector that's in that direction. And we'll get to that. That's important. We compared basically the electric field and the magnetic field, and both had a constant at the beginning. And then both were inverse square. What's interesting is that although the electric field tend to be radial, they point radially away from the charge if it's a positive, or radially towards the charge if it's a negative. The magnetic field is tangential to a circumference. So it's with a curl. We describe it with a curl. This is diverging, and this is curling, if you like. So probably mentioned those in Calc 3. And then I said, well, let's do an example of Boyau-Savart. And what I said was, in the day, I started writing down solutions because I noticed that sometimes people would have the wrong, like a typo here. And I was never sure if it was me writing it wrong or them copying it wrong or whatever. So I thought I'd basically just try writing them down before class, so I know they're right, and giving you them so that I know you have them, and then going from there. So anyway, what I was saying, the final bit I was saying before I had to go back, was that the difference between physics calculus and calculus is that we use symmetries whenever possible, and we take stylized questions. And it's not that the calculus that you learn in calculus class is irrelevant, it's that we don't want to get bogged down with that calculus. It's not that engineers don't know any of that calculus, they do. But knowing this, and then knowing your deeper calculus, you'll be able to do, you'll be able to progress even further. And the other point that I just want to make sure you understand is that it's not that if you go to other classes you'll do all the really complicated stuff, and it's only in HCC we do all these cheating. If you look in the textbook, this is what they're doing by and large. The idea is calculus, and physics is physics with calculus. It's not calculus with physics, it's physics with calculus. So we use symmetries. So here's an example. So for instance, I could use any shape of wire, and I could have a current flowing through. I could pick any point, and I could do Boyau-Savart. In principle, it just works fine. But it's a long, bit of a tedious problem, etc., etc. So what we say is, let's just get to the principle of it. Let's use a nice symmetrical wire around a point of interest. And so we use the middle of a circle. And that way, if you think about it, a lot of symmetry. Every point on the wire is the same distance away from the center of the circle. And in every case, your ds, your little wire length vector, and your r hat vector. I put the r hat at the wrong place there. I wish I'd done it. It's the same thing, it's just the opposite sign. But I wish I'd put it there on the wire. R hat is at 90 degrees to your ds. Two very nice symmetries to simplify the problem. So this problem says a current carrying wire is bent into a complete circle. And I can tell you now, what I'm going to do is I'm going to give you a fraction of a circle, or maybe 1.5 circles, or maybe 17/16 circle, or maybe 15/14, or whatever, whatever I do. Current carrying wire is bent into a complete circle. Use Boyau-Savart method as taught in class to show that B at the center of the circle is. Now, I wouldn't give you that as a test question. I'd say, what is the B at the center of the circle? And you'd figure it out. So first of all, we visualize. So I have my circle, and I have my little length of interest, my ds. It's the length of the current carrying segment of wire. And I have my little unit vector pointing along the radius towards the center, which is my point of interest. And I note my current in there, I note my radius of my circle. And I say, well, Boyer-Servat's law says, I've got to know this, it says that B is equal to a constant, mu naught over 4 pi, times the constant for this problem, which is the current. It changes from problem to problem, but the constant for this problem doesn't need to be integrated because it's the same throughout. Integrated with what does change, which is the little ds changes as I go around the circle. Not length doesn't change, but the direction of it changes. And my unit vector pointing from the ds of interest to the center of the circle, r hat. Different directions for each different one, so yeah, they've got to be integrated over r squared. Now, in this example, r squared is constant. So I've got to recognize that. My r is constant, my radius. Sorry, I called it big R in my diagram and little r in my generic thing. I'll substitute in at the end. So this r squared is constant, so can come out. So I have mu naught I over 4 pi r squared integral of ds crossed with r. This is not so bad now. So I have my ds and I have my r. It's the r hat, isn't it? And I look at those and I say, well, look, they're at 90 degrees to each other. By definition, on a circle, your ds is a tangent and your r hat is the radius, so they're at 90 degrees to each other. They're perpendicular. And so when I think about it, this would be, in terms of magnitude, ds times r hat times the sine of 90. And the sine of 90 is 1. So I would have ds crossed with r hat would give me ds magnitude times r hat magnitude, let's put those just in brackets, times the sine of 90 degrees, and that's going to equal 1. So that's that taken care of. And to make it even nicer, my r hat has a magnitude of 1 because it's a unit vector. So this just comes down to be ds under these circumstances. So I get, so B is equal to mu naught I over 4 pi r squared, the integral ds. Okay, the integral ds is simply all these little ds bits added together, which is going to be my circumference, which, as I know because I've learned all my little equations, is 2 pi r. So just to cancel, the 4 and the 2 gives you a 2 on the bottom, and the pi goes away. And one of those r's gets rid of that r squared. I have mu naught I over 2 pi r. And in this case, I know that r equals big R because that's what it's called. And so I say mu naught I over 2 pi over 2 times big R. So there I have it. In a typical test question, I'd give you the value for the radius, and I'd give you the value for the current. And you could work out the numerical value. One little thing I've noticed again, I'm sorry, these are just, you do them, and so notice how I did my ds going in a clockwise direction, and I did my I going in a counterclockwise direction. That can't be right. ds points in the same direction as I. So that's just me, just been a bit, messing with my diagram at the very end, and just been, a bit asleep at the wheel. They must be in the same direction, yeah. Just a little point. I don't want that to worry you if you start thinking about it. Okay, so that's a typical question, okay? That's what they're like. Let's do one together. So a current carrying wire is bent into a semicircle. So I still give you a diagram. I don't like my diagrams that I give you as the teacher. I always do my own diagram again. So there's my semicircle. There's my point of interest. Let's have a look. Determine the value of V at the center of a semicircle. Assume that the current flowing through the wire. So let's have I is equal to 5 amps. And let's have the radius r is equal to 2 meters. Okay. Let's pick a little ds. And let's pick an r hat. And there's an r. Okay. Let's do our right-hand rule. Let's do our corkscrew rule. The ds is in the same direction as the I, so put your thumb in the direction of the ds, yeah? And twist. So I'm over here, and I got my thumb going in the same direction as the ds, and my fingers are twisting. So they come out of the paper on this side, and they go into the paper on that side. Agreed? So will this be the magnetic field going out of the paper or into the paper? Into the paper, yeah. Because we did that corkscrew rule. And will that be a... how will I symbolize that? Yeah, it's the arrows going away from me. So I would symbolize that by that. It's the arrows that are going away from me, yeah? So that's a nice, not required for this question, but it's a nice thing to reinforce. What is required for this is that I know my Boyer-Servat's law. So I say that the magnetic vector is equal to, that constant, it was mu naught over 4 pi, and then we had the current. So I'm going to leave my current, I like to leave my letters in. And then it's going to be the integral, and it was, which way round was it? Good. ds cross r hat. And in the notes it says r vector, but it's r hat over r squared. So that's going to get me some credit. And then I go, okay, well, b, I'm going to do a couple of things first. I'm going to say, well, if you notice this, I'm going to say ds is perpendicular to r hat. R is constant. R hat equals 1. And it'd be very nice, I'd love it if you can say, so ds cross with r hat is equal to ds r hat sine 90, which equals ds times 1 times 1, which equals ds. That's a very nice understanding. That's the physicsy bit. I don't know if in the math they care about that so much, but I care about that a lot because it's the justification for the next step. So then I say, well, okay, in that case then b is equal to mu naught I over 4 pi times the integral of ds, which equals mu naught I over 4 pi times, now, yep.
You forgot r squared.
Oh, over r squared, yeah. Let's not tell anybody about that. So r squared. And then, okay, I want my length. So my length is going to be 2 pi r, but it's not a complete circle, is it? It's a semicircle. Oh, it's a half of 2 pi r. Yeah, just a half of it. So this is going to be, well, let's take all this account. So that's going to be, oh, okay, that's going to be mu naught I over 4r. Mu naught I, those cancel, the pi's cancel, over 4r. So b is going to equal mu naught. The current is 5 over 4 times 2, which would equal 5 over 8 mu naught Tesla. And I don't mind on a test if you leave it like that. I don't like square roots stuck in there. Sometimes people give me square roots in their answers and all that. I don't like that so much because that's, you got to do some calculations there, but I can do 5/8. You don't have to do it. Sometimes I say to everybody, work it out for the decimal, and I realize I'm trying to get the people who are leaving the square roots in. So I might as well just say, don't leave the square roots in, You can leave me with a fraction, not 5 fractions to multiply together and added with 27. But, Most common mistake on when there's a letter been left behind is people just forget about the units. And that adds up on a test. That can be a real pain, actually. What can I do to make this a little bit more interesting? What I can do is... Well, anybody got a suggestion? What can I do to make it a bit more interesting? Sorry?
Give it more than enough for one circle.
No, that's just... yes, I can. But, So let's say that you have 3.5 circles. You'd go 2 pi r times 3.5. If you know the circumference and supposing it was 1/8 of a circle, it'd be 1/8 times 2 pi r. If it was 17/19, it would be 17 divided by 19 times 2 pi r. So it's not that. No, I wouldn't change that because that changes the whole thing. That would be a real pain. Yeah. No, I can just give you the length. I can tell you it's a semicircle, but not tell you it's a radius, tell you its length. And then there's this whole thing about, well, the integral ds is the length, so shall I just substitute the length in for that? But then I've got to work out what my r is, because I've still got an r in my answer, So if I give you the length, what I would do is I would work out what r is. And then I'd do this. You know what I mean? Rather than falling between two stools. Just work out what r is. Give you the length. 8 meters equals a semicircle. A half 2 pi r equals 8 meters. Rearrange. Then do this. Work out nicely. Then you're doing the same thing over and over again. Because what I noticed was when I gave people length, they fell apart. Because they were like trying to change the middle of the problem. And they were like, well, I've got my L. And then they were forgetting about the r because they hadn't worked out the r. Or they couldn't figure out the r because they didn't visualize it. So that's the one thing I can do that makes it a bit more interesting. And this. This is, I would not ask you this. I don't think I'd ask you this on a test. I wouldn't. Because I don't practice it with you. But I want to show you it. Because it's not anywhere near as bad as it seems. It looks horrendous. R squared plus x squared to the 3/2. I can't even imagine where that comes from, etc., etc., etc. And the reason why I want to show you this is in part because it's like me going to the gym a little bit, It's kind of like, but also it's like I want to kind of encourage you to come out of like that corner that you tend to go to when you see something and you go, man, where did that come from? Especially with algebra. I got friends at USF who love all letter questions. They think they're easier than the numerical questions. And I'm never sure if they've been genuine or just been, kind of like, just gilding the lily a little bit. Most people find all letter questions to be quite daunting because the answer's algebraic and it's like, it's almost like looking into a skeleton and, it's like, it's not just 27 and I got 32. Man, I must have made a mistake somewhere. It's like, man, and I think it's partly because people sometimes have a bad experience at the beginning of algebra where they get a whole bunch of questions and they're just like stuck on and it's like they don't know where to go forwards. But in a way, the bare bones kind of gives clues about what's going on. Have you seen anything like something squared plus something squared with a square root somewhere near it? What was that when you dealt with it? Something, not in physics, but in math. Something squared plus something squared equals something squared. What? Pythagoras. So I look at that and I go, oh, Pythagoras is going on here. I just know it in my bones because it's got that very familiar stuff. Why is the 2 in front of it? I have no idea. That'll come later. But I got a good feeling Pythagoras is coming here. So then so let's do it then. So we're going to turn around and say, okay, well, this is Boyer-Sabat. So I'm going to say, well, B is equal to mu naught I over 4 pi times the integral of, let's remember, it was, which way around was it? It was ds crossed with r hat over r squared. So that's that, okay. And let's have a look. So for that little guy there, I can work out I got to integrate over this the entire thing. So I'm showing a little ds, and I'm showing the result of the little ds. And then I go around a little bit, and I have another one of these guys. And I go around a bit, and I have another one of these guys. And I go around. Can you see I'm going to make a fan up of these vectors? Each ds is going to give me another vector. Can you see that? Does that kind of make sense? So over here, that little ds is causing that vector, and that little ds is causing that vector, and that little ds would cause that vector. So we get this like cone of little answers, you know. In potential, there was just an answer because they were all scalars, but now they're vectors. So I've got to take these into account vectorially. It says a current carrying wire is bent into a complete circle. Use Boyer-Sabat's law method as taught in class to show that the magnitude of the x component. If I draw this from the side, I have my ring, and then I have boom, 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 and then I have boom, 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 and then this is x. And then this is r. And there's my point of interest. So this here is the little r in that equation. And this is my r hat. And this is my point of interest. And so by the right-hand rule, by the corkscrew rule, I'm going to get a component dB that looks like that. So I've sliced that top diagram vertically, and that's what I see. I see the current carrying wire, there's the top part of it, and then I cut through the current carrying wire in the bottom part of it. And then here's my axis, there's the plane, here's my axis, here's my x, and here's my r, and etc. Yeah? Make sense? So, okay, well, here's the thing. R is constant for all the DS's. Can you see for every one of these? It's the same distance. It might be at a different angle, but it's the same distance because it's on the axis, yeah? Yeah? Yeah. Oh, so B is equal to mu naught times I over 4 pi r squared times the integral ds cross with r hat. And then if I look at this top bit, my ds is say in that direction, and my r hat is still at 90 degrees, ds and r hat. It's not that this is vertical and that's horizontal. This is horizontal and this is at some angle, but that angle there between the ds and the r hat is still at 90 degrees. It just swung out. Rather than pointing towards the middle of the circle, I'm pointing further down the line. So, okay, that then means that ds is perpendicular to r hat. So that means that ds cross r hat will equal ds r hat sine 90, and that equals 1, and that equals 1. So, this is all right. So B is equal to mu naught I over 4 pi r squared times the integral of ds, which equals mu naught I over 4 pi r squared, and the integral of ds, this is a complete circle, isn't it? That's going to be 2 pi r. Okay. Oh, got to be careful. 2 pi big R. This 4 pi R squared is using that R. That R. This 2 pi R is using the circumference of this guy, which is 2 pi big R. They're not the same. That's a little pitfall you've got to watch out for. Okay. Let's simplify. So this is going to be mu naught I. That 2 pi over that 4 pi becomes 2 R over R squared. Well, let's have a look. I got my mu naught and I got my I. I got my 2's appeared, which is kind of nice. But, you know, what this is, it's a sum of all these guys. But if you think about it, I'm going to draw the other one. I'm going to draw the two opposites. So this is dB and that's dB. And for every pair that are on opposite sides, that blue one and this one and that one and that one, there's going to be the same situation where the component in the, if you like, the vertical directions are going to cancel, and I'm left with just the components in the x directions. Does that make sense? Oh, so I need to multiply this by the component. Well, the component is going to be cosine, and we'll call that that. So I worked out my dB, and I want to work out what that component is, and it's going to be the dB times the cosine. There's my dB, the integral of all my dBs, times the cosine of that angle. So that angle. Now, okay, so my B is equal to mu naught I R over, let's express this little r, so 2, and let's express this little r in terms of big R and x. So that would be the square root of big R squared plus x squared, and I got to square it because of that square. Okay. So that's that bit cleared up, and then I got to clear up this cosine at. Cosine at is the adjacent. So if that is the at, then big angle, little angle, big angle, little angle, big angle. So there's my same angle. So that angle there is the same as that angle there. And if I'd not drawn it at 45 degrees, it would be very clear. Yeah? But big angle, little angle, big angle, little angle, big angle. Agreed? So that angle there is the same as that angle there. And oh yeah, cosine of that is equal to my adjacent, which is r, over my hypotenuse. And my hypotenuse is the square root of r squared plus x squared. Oh! I think I'm just about there. Mu naught I r squared over 2, and this is going to be r squared plus x squared, and not to the, this is squaring square root, which is it. It times the square root is not, it's to the 1 plus a half is to the 3 over 2. And you got it. Yeah? So I won't ask you that on a test, but I don't want you to be kind of feeling like I'm never going to be able to do that. There was a time when I couldn't do that, and I just, stuck with it. And in a way, the more complicated it looks, the more hints it's giving you. Okay? Agree? Okay? Agreed? Okay. Okay. So expect a Boyer-Savart question. Might give you L rather than R, might give you more of a circle or less of a circle or whatever. It's going to come. Next thing, magnetic force between two parallel currents. Again, I pulled this out of a hat, but it kind of makes sense. One current, they're both carrying current. They're both carrying current, but we pick one of them as the parent and one is the child. So let's say this one is the parent. So that's the parent. That's the one I'm going to look at. And you say, what direction does that current flow in? And it's flowing to the right. And I use my right-hand rule. And I recognize that it's going to create a magnetic field. And that magnetic field I can represent as a circle. That's my B. And it comes up. And when it goes through here, it's basically pointing in that direction. Looking at it from this end, my current is coming towards me. So I'd represent the current in that bottom wire by this end. And I would draw a loop around it. And I would say, well, where's the other wire? The other wire is there, and my B is in that direction. Because my current's coming towards me, and I'm curling my fingers round in a counterclockwise direction. So there's my B. Now I say, well, what's the current flowing through this second wire? Oh, this one is also coming towards me because of that. So now I can do my cross product. QV cross B. The V is coming out of me on the top. I'm going to cross in direction, curl my fingers in direction with the B. So my force is in that direction. Can you see that? I look up here and I say, well, you know, that current, that top wire is coming towards me. And I've got to curl my fingers so I can point towards my B. And my B is in that direction, so my force must be pointing downwards. So that arrow downwards comes because of that. If you like on here, I'd say point my you know, I cross B. It's this, you know, I L cross B. So there's my L, and I've got to curl my fingers so it points in the direction of the B, so my thumb points downwards. With a bit of practice, what you realize is that, so on that diagram, the top diagram, is that an attractive force or an repulsive force? Is the top wire being pulled towards the bottom wire or away from the bottom wire? There's my force. Is it attractive or repulsive? It's attractive, isn't it? And if I did a cross here, again, I would have my magnetic field would be like that. And I'd say my current's going into the page, and so my magnetic field for that top wire would be in that direction. There's my B. Everybody okay on that? And then I say, well, what's the current flowing through that top wire? Oh, look, this is also into the page. I decided. Now I do, oh, if it's going into the page, then my L is into the page, and I've got to turn my hand so my fingers are curling towards the B. And I get another force going downwards. So is that going to be an attractive force or repulsive force? Is it pulling towards the second wire or pushing away from the second wire? There's the first wire, there's the second wire, here's my force, pointing downwards. It's attractive again, isn't it? And if I go over here, I'll do it down the bottom. So if I have a third option, let's do that. We decided that there's my second wire. My B goes in that direction. Now let's say I don't have them flowing in the same direction. The currents are going in opposite directions. So this wire here has the current flowing in that direction. Now L cross B. My L is going into the page. I turn my hand so I can curl my fingers towards the B, and my force is pointing upwards. Is that going to cause attraction or repulsion? It's pointing away from the bottom wire, so the wires are going to pull apart. And if I just finish the pattern off, and if I do that, I get a nice curl, do my right hand rule, my B is in that direction, I do my L cross B is my wire. I'm going to have this in the opposite sense as well, so that's going to come in out of the page, curl towards my B, there's my F. Again, a repulsive effect. Doesn't matter which one of these two wires. You'd pick one and you draw the circle around the other one. It's like, doesn't matter. You need to be able to do that skill, or you need to be able to remember, in addition, you need to be able to remember, I can work them out, is that opposite directions of current repel, parallel directions of current attract. Doesn't matter if they're coming towards you or going away from you. Doesn't matter if they're coming towards you or going away from you. They're going to be attracted. Parallel attracts. Yeah? How much does it attract? That's given by this equation where this is L. I'm sorry, it's like it's one of those things where the fonts get to look similar after a while. This is the force per unit length. And we say the force per unit length is equal to mu naught I1, that's the current in the first wire, times I2, current in the second wire, over 2 pi times A, and A is your separation. Looks a bit like 2 pi r, like a circumference, and there we've got a circumference that we're playing with, so yeah, you can kind of somewhat remember it like that. When both wires carry current in the same direction, it's attractive. When the current in the wire flow in opposite direction, it's repulsive. By the by, one of the reasons why they like to talk about this, apart from the fact it's a kind of neat effect, is that if you want to define the amp, it used to be you would actually define the amp as being the flow of 1 coulomb of charge per second. That's difficult to actually set up and control and do. And so how do current meter manufacturers know where to set the calibration on their meters? I mean, how do they know? At some point, standards have to be referenced back. And it's very difficult to use a standard like a coulomb flowing per second. It's a real pain. So what somebody came up with was, let's say that when we have two long parallel wires that carry identical currents and are separated by 1 meter, 1 amp flows when the force they feel is 2 times 10 to the minus 7 newtons per meter. So it's like a secondary standard. And people like the National Institutes of Science and Technology, or in Britain it's called it's in Teddington Lock, it's called the National Lab. They're responsible for weights and measures and standards, and they frankly are looking for better ways of standardizing things. It might not seem obvious, but when you go to Publix and you get like a half a pound of meat, somebody has to check to see that scale is not out of calibration, or else, frankly, there's no guarantee that the scales won't be out of calibration, you know. So that's done by the government. That's, you know, there are some things that are best done by the government. That's one of them. It's like, you know, you need you need an uninvolved person who is only interested in the common good, you know, to do that. And so you want the speed of light, that's done by NIST. You want a farad, that's done by NIST. And they send out secondary standards, which then manufacturers use to calibrate their systems. And every now and then they'll pull back the secondary standards and send out a fresh one to calibrate it. And they'll come around and they'll check. And if you're making capacitors and you're saying that 2 farad capacitor, they'll check it and say, well, actually, that's only half a farad, you know, you get back in line. So forever they're looking for better ways, easier ways. Speed of light is measured by, a second is measured by so many wavelengths of a certain color of light. It's no longer how far you go around the sun or how much you spin by. It's measured in a much more scientific way. Consider two parallel wires. One wire carries a current of 5 amps to the right. So let's do 2 wires, 5 amps. The second wire carries a current of 4 amps to the left. So 4 amps. Wires are separated by 2 meters. 2 meters. Are the wires attracted towards or repelled by each other? So let's just do this. We'll say that's going in there, that's going in there. That's going into the board, so my magnetic field goes in that direction. There's my B. I do my L, cross my B. Let me just do that right. Yes, that goes in that direction. Do my L, cross my B, and that is going to be F. So that is going to be, which is that going to be? Attracted to or repelled? It's repelled, isn't it? Yeah. Because it's pushing away from. You know, there's one on there, there's one on there. They're going to go away from each other. They're repelled. What is the magnitude of the force? This should be the force per unit length. That's my bad language. F over L is equal to mu naught, because it's to do with magnetism, I1, I2 over, and it's something to do with like circumference of a magnetic field circle, so I'm going to say 2 pi A. This is mu naught. Doesn't matter what direction it's in, it's just 5 and 4 over 2 pi times 2, which equals 20 over 4 pi mu naught, which equals 5 mu naught over pi, and that would be newtons per meter. Cool? Yep. Yep. Ampere's law. We've been at this about an hour since class began, so I'm going to take a break because this next bit's important.